Hey everyone. In this video, I'm going to introduce some regression models for ordered categorical data. And it turns out that in political science applications, we have a lot of outcomes that are indeed ordered categorical. So, for example, if you're working with survey data and you ask people whether they agree or disagree with certain policies, oftentimes these agree-disagree items are measured on a 5-point scale from strongly disagree to strongly agree or something like that, right? Or we can have other types of Likert scales for other types of attitudes that are also on like 5-point scales or 7-point scales, right? And these are essentially ordered categorical outcomes, okay? In the sense that they're discrete outcomes, different discrete outcomes that have an inherent ordering to them, okay? Even beyond kind of the survey realm, we could think of, again, if we think of like conflict studies, and we could classify certain conflicts or certain events as no conflict, or there's a compromise, or a non-lethal conflict and a lethal conflict or something like that. Again, we could categorize certain states in like either interstate conflict or intra-state conflict in different categories with a certain inherent ordering that is kind of proportional to the intensity of the conflict or something like that, right? So depending on what your substantive field of interest is, there are lots of examples of outcomes that we usually measure and that we want to predict that are discrete, categorical, with an inherent ordering. Okay, so now the question is, how can we model these outcomes? How can we best predict these types of outcomes? Okay. So the example that I'm going to go through here is just to illustrate how we can go about modeling these ordinal or ordered discrete outcomes is to predict party identification. And what I'm going to use is a data set similar to the one that we worked with in the past, but an updated version of the American National Election Study. Here we're just looking at the year 2002, so this is basically a midterm election study, basically, not during the presidential election. And what we're going to do is we're going to predict party identification, which was here just measured on a 3-point scale, so either Republican, Independent, or Democrat, okay? And so in this case, we're going to kind of assume an inherent ordering in the sense that we could think of these as, from an ideological left-right spectrum, Democrat, Independent, and Republican as inherently ordered, okay? And so now what we're going to do is we're going to try to predict basically belonging to each of those, whether respondents belong to each of those categories, either identifying as Democrats or Independents or Republicans, based on a couple of characteristics. We have ideology, we have education, we have age, race, and gender. Okay, and so this is the basic setup that we're going to use. You can, again, as always, kind of go through the code and change around the model specifications as well, or look at other examples as you like. So again, the outcomes here are discrete. We have just 3 different outcomes, but we assume an inherent ordering, basically consistent with like where these parties and independents lie on the ideological spectrum. Okay, so the dependent variable is categorical with J number of categories that follow an intuitive ordering. Okay, so the first question is, if we have this setup, if we have an outcome like this, yeah, how can we model this outcome using the tools that we have learned so far? Okay. And the tools that we've learned so far is basically linear regression, OLS, or logistic and probit models for dichotomous outcomes. Okay, and each of those, of course, we could use, but it has certain downsides and certain potential issues, right? If we're analyzing an outcome measure like this that is categorical or ordinal with an inherent ordering, but discrete, we have basically a couple of violations of the standard linear model. One is that we definitely have heteroscedastic errors similar to in basically introducing heteroscedasticity as soon as we use the linear probability model. So we already know we're basically violating that assumption. But there are additional issues. For example, if we just analyze this outcome as continuous, what we're making is the assumption that there's basically an equal distance between each of those categories. In other words, if we just assume that this party identification measure, which has the outcomes 1, 2, and 3, is just continuous, we're basically assuming that the difference between, changing from 1 to 2 or from 2 to 3 is exactly equivalent. Okay, and is exactly equivalent in the sense of how the predictors that we're going to use are kind of associated with changes from one category to the next. Okay, in the context of party identification, this might not be so problematic. Moving from Democrat to Independent versus Independent to Republican might be fairly equivalent. But if you have other types of items, particularly, if you have different types of Likert scales with like more than 3 categories, then this assumption might actually be violated, right? And these might be things that you want to take into account if you want to predict your specific outcome of interest. Okay. The other issue with linear regression in the context of these ordinal outcomes is that we can produce nonsensical predicted values, and this is kind of equivalent to the argument that we made for the linear probability model. In particular, if we have just a basic linear regression, we can have predicted values that are outside of the range of values that we actually observe in the data. Okay, so we could have predicted values of, in our example here, we could have predicted values that are smaller than 1 or larger than 3, and those would obviously be kind of nonsensical in the context of our actual outcome that is bound between 1 and 3. Okay, so obviously OLS has some potential disadvantages and potential issues, but how about using just logit or probit? Okay, we could dichotomize, either combine categories or throw omit one category, okay, and then just run a logistic regression or run a probit regression. We could do this. The only problem is that we're throwing away information, and by throwing away information we will always lose efficiency. Okay, so this is also not an ideal strategy if we have an outcome that is categorical. Just throwing away information usually will not lead to very good predictions. Okay, so how can we then come up with a better model in the context of generalized linear models that represents this underlying data generating process and allows us to predict different categories that are discrete but have an inherent ordering to them. Okay, and in order to explain, kind of derive the model, one way to think about this is to go back to this latent variable specification that we talked about when we derived the logistic regression. Okay, remember the latent variables specification for logistic regression. We made this assumption that there's an underlying unobserved latent variable that we're modeling with our linear predictor, and then we're making assumptions about kind of we make additional assumptions about the underlying distribution of this latent variable that is unobserved. And then based on that distribution of that unobserved latent variable, we can compute predicted probabilities for observing a 1 or observing a 0, right? And in order to now derive a model for more than 2 categories, all we have to do is basically extend this latent variable specification by having not only one threshold, but basically introducing multiple thresholds and thereby computing probabilities not just for y being equal to 1 or being equal to 0, but for y being equal to each of the outcomes that are included in our, or that are basically included in the outcome. Okay. So in other words, in order to specify this ordered logistic regression from a latent variable perspective, we start the same way we started with the logistic regression. we just define a underlying unobserved latent variable, which we call y star, and this is a continuous, as I said, unobserved variable. Okay, and then we can define our model through its stochastic and systematic component. We have our y star that follows some probability distribution conditional on its mean, and we model this mean based on our linear predictor beta prime xn. Okay, this is equivalent to the latent variable specification for the logistic regression that we talked about. Okay, the only thing now that is that the observation mechanism is slightly different, right? Remember, for the observation mechanism for the dichotomous outcome, we just had one threshold basically, which we call tau, in order to compute the probabilities for y being equal to 1 or y being equal to 0. Okay. The only difference now is that we have multiple thresholds, and we can have probabilities for y being equal to 1, 2, and 3, and so on. Okay, so assuming here we have j categories, that means the outcome yn ranges from 1 to in our case 3, but it could be a larger number of categories. The number of thresholds that we then have to kind of estimate in this observation mechanism is j minus 1, right? Which makes sense if we have 5 different categories and we need to distinguish between these 5 different categories. We need 4 thresholds in our unobserved latent variable. Okay, and we're assuming, of course, that these thresholds follow this ordering, right? So tau 1 is smaller than tau 2, is smaller than all the other taus, and then tau j is the highest threshold, right? So that kind of invokes this ordering in our outcomes. Okay. To kind of think about this visually, we can kind of plot our unobserved y star, or underlying latent variable, for different values of x, right? And similar to our latent variable specification of the logit model, we have a distribution around this y, or the y star follows a certain distribution with a conditional expectation conditional on x. Okay. But now when we look at this density, basically, we don't only have basically one cut point where we have a probability of y being larger, y being equal to 1, and or y being equal to 0, but we have, in our case here, we have 3 thresholds, so 3 taus. Okay, so the probability of y being equal to 1 is basically, for x1, is basically the probability mass here that is below tau 1. Y being equal to 2 is the probability or the density between tau 1 and tau 2, and equivalently y equals to 3 is the probability mass or the density between tau 2 and tau 3, and so on. Okay, so as we can see here, for x1 we have a fairly large probability of y being equal to 1, and a slightly smaller probability for y being equal to 2, and the probability of y being equal to 3 or 4 is essentially almost 0. And as we increase our x, the conditional expectation of y star increases. So if we're up here, we see the probability of y being equal to 1 is almost 0, y being equal to 2 is slightly smaller than 0.5, y equals 3, slightly also around 0.5, maybe slightly smaller, and then we have an additional probability of y being equal to 4. Okay, so in other words, conditional on our x, we have our expected y star, and we have our assumed distribution for y star, and based on that distribution we can then compute the probabilities according to these thresholds. Okay, and again, this is now just looking at one specific cut point. Now, assuming, for example, we only have 3 different categories, we could just compute the probability mass up to tau 1 to compute the probability of y equals 1. Between tau 1 and tau 2, the probability of y equals 2, and larger than tau 2, we have the probability of y equals 3. Okay, so again, make sure to kind of go back to the latent variable specification of the logistic regression to compare and see that this is basically just an extension where we add additional thresholds in this observation mechanism. But the underlying logic is essentially the same. We have an underlying latent variable, and based on the distribution of that latent variable and the thresholds in in that latent variable, we have an observation mechanism with probabilities of y being equal to each of those category outcomes, essentially. Okay. All right. So how do we do this in R? Again, using our example of predicting party identification. If we use Stan, and if we want to do this in a Bayesian framework, we can use the command stan underscore POL R. It's not the stan underscore GLM, but stan underscore POL R for polytomous, so multiple outcome regression, basically. And our model formula is the same as or similar structure as before. We have our outcome measure, party ID, and we have our 5 predictors. We have to specify a prior for our square, and then we can again omit the sampling output. Okay, with refresh equals 0. Okay. If we want to do this not using stan but using basic frequentist maximum likelihood estimation, again we can rely on the mass package. The command here is polar, so we just omit the stan underscore, and the command is basically the same. If we include this argument Hessian equals true, we can basically in the output get the Hessian matrix as well, which will help us if we want to simulate quantities of interests, which we might talk about a little bit more in the Q&A session. Here we're specifying that this is a logistic. We could also have an ordered probit, and then we could include the method equals probit here. Okay. What does this result look like? Here we're just focused on the Bayesian estimation using stan. Basically what we see here is the coefficients for the linear predictor. The linear predictor now is basically the change in this underlying latent variable. So with higher values of this predictor, that means we have a higher probability for the higher categories in our outcome measure, right? So we can't directly interpret these as just by itself as probabilities. We only know that, you know, if education here is a positive coefficient, that means comparing two respondents that differ in education, the respondents with higher levels of education have a higher probability for y being equals to 2 or 3 rather than 1. Okay. Similar for negative coefficients, we know that there's a higher probability. For example, this is a dichotomous indicator for African American respondents, and we see that they have a higher probability to be independent or Democrats rather than Republicans, for example. Okay. The important thing here, of course, is that in addition to the coefficients, we're also estimating these cut points that we talked about in this latent variable framework, right? And this is basically the cut point or the tau at which the observation mechanism switches from y being equal to 1 to y being equal to 2, and y being equal to 2 to y being equal to 3. So those are those tau cut points that we're estimating. Okay, and by virtue of estimating those based on the data, we can also basically evaluate whether, you know, a switch from 1 to 2 is equal to a switch from 2 to 3 is equal to a switch from 3 through 4, and so on, right? While in the linear regression framework, we basically made the assumption that you know, a 1 unit change in y is constant and is basically equivalent across the range of y. We can now kind of test this assumption directly or evaluate this assumption by examining the cut points and examining whether these cut points are equally spaced. Okay, going back to this visualization, we see, for example, the cut point tau 2 and tau 3 are closer to each other than tau 1 and tau 2. So there's basically a constant change in the probability depending on the value of our underlying latent variable. Okay. Again, you can check the frequentist estimation and see that it compares or is basically equivalent if we're using standard priors. Okay. Of course, we can just think about the direction of the coefficients based or the kind of the direction of the coefficients if we want to interpret these ordered logistic or ordered probit results. But ultimately, if we want to really have an idea of kind of the substantive implications of each of those models, ultimately what we want to do is basically use the same model, use the same methods that we kind of learned in the context of logistic regression and compute predicted probabilities and maybe look at first differences, changes in predicted probabilities for individual categories, and then visualize those, right? So for example, we could kind of create these stacked or cumulative predicted probability plots where we compare a predictor that is increased from its minimum to its maximum, and then for each of those values in the predictor we could compute the predicted probabilities for each of those individual categories from y equals 0 to y equals 4, for example, right? So compared to just the pure coefficients, a cumulative predictive probability plot such as this one gives you a better kind of substantive idea of what exactly the effect sizes look like. Okay, and so in our Q&A session, we're going to talk about some examples of, for example, creating these cumulative predictive probability plots in order to interpret our ordered logit or ordered probit results. Okay. All right, so that concludes our quick overview of ordered categorical data. In the next and last video, I'm going to talk about unordered categorical data.